All right, well, it's 8 o'clock, so let's get started. The first bit of housekeeping. Yeah, you're going to be all alone.
You're on that side of the class, that's the problem.
I was cleaning out my desk, found an entire stack of graph paper that I have never used a graph paper in my life. I have no need for it now. If y'all use it, if you need it, if you want scratch paper, help yourself. Other bit of housekeeping here. Megan Walker. Jeremy Reichert. Tyler Koshaway.
He'll be here in about 2 minutes. That's how you like to know people.
Jesus Antonio Rodriguez. I tell you, some of y'all just have names that are fun to say. Val Peterson.
Right here.
Zach Woodard. Matt Letney. Jacob Sanchez. Jimmy Flood. John Caldwell. Deja McClellan. Stephen Turner. That's Tyler.
Like a minute and a half. It was only a minute and a half, not 2.
Tyler Koshaway.
I'm here though.
You bet. Stephen Turner.
Oh, yeah.
Oh, looky there. Deja McClellan. It's another one with a name that's just fun to say. No, Deja.
I never get all the keys together when I do that.
Are you Megan Walker? No. Derek Heineman. I'm going to make this thing sprain an ankle. Michael DeBach. Jesse Martin. Here, meet me halfway before I give this thing before I make it blow a circuit. Travis Black. Jacob Childers. Christopher Macklin. Kyle Kohler. Okay, I just said it there on my book. Kyle Kohler. Jory Owens. And still no Stephen Turner. Well, I thought my folder was going to finally be empty. It's emptier anyway. Here you go. Why don't we pass that around, please? Does anyone else have homework they want to turn in? Does anyone have any questions from the homework? What you got? from assignment 1 or from assignment 2? That's what we're going to go over today, yeah.
Number
43 on page 206? Say again? Okay. Looking for the inverse cotangent of minus square root of 3 over 3. Okay, the cotangent, we're looking for the angle whose cotangent is minus 1 over the square root of 3. What does that mean? If the cotangent is minus 1 over the square root of 3, that means we're looking for the angle whose tangent is minus the square root of 3. Right? So turn back over to the handy-dandy chart on page 179. And where do we find tangent equal to the square root of 3?
Pi over 3.
At pi over 3.
That's what I got for an answer. It was negative pi over 3. But the book says it's 2 pi over 3. And that's where I was confused.
Because you were looking at the cosine. You were looking at the positive square root of 3. At minus 60 degrees, okay, a couple of things going on here. Look, I'm finally going to use a piece of graph paper. A couple of things are going on here. First of all, we're doing an inverse function, which means we're restricted. We have a very restricted range that has to be between. What's the range of the inverse cotangent function? What's the range of the inverse tangent function?
So the range of this inverse is negative 1 over 1. Or no, the inverse is 0 to pi.
The domain of the domain of the tangent function is the range of the inverse tangent function, which means we're looking for the domain of the inverse would then be minus infinity to plus infinity, but the range would be minus pi over 2 to pi over 2. No, for tangent. No, you're low. No, we're gonna get there. See, this is one of those. Everybody follow along carefully because this really does get confusing. Let's go back and find the graphs of the cotangent function. See if we can find that. tangent function has a domain, is undefined anywhere at minus pi over 2 and multiples thereof. Here's the cotangent function. It's on page 163. But if you'll notice when you start graphing the cotangent function, everything shifts right by pi over 2. So its domain is going to be from 0, the domain of that first fundamental period is going to be from 0 to pi for the cotangent function. Okay? Now, since the restricted domain of the cotangent function gives us a range of the inverse cotangent function from 0 to pi. Now, where in that range from 0 to pi would you find a cotangent of minus 1 over the square root of 3, or stated differently, a tangent of minus the square root of 3? At pi over 3, you would get a tangent of square root of 3, and you would in fact get a cotangent of 1 over the square root of 3. But we want negative 1 over the square root of 3. That means you would have to go into quadrant 2 between pi over 2 and pi. And at 2 pi over 3, you would find the tangent is minus the square root of 3. Now that's not going to show up on your inverse if you try using the inverse tangent function to find this value. And on your calculator, you're restricted to sine, cosine, and tangent. So if you're working with secant, cosecant, or cotangent, you have to work with the definition and deal with the reciprocal to go back and use tangent or whatever to find it. But when you switch over to from the inverse tangent to the inverse cotangent function, you're actually shifting from minus pi over 2 to pi over 2. You're having to shift everything from 0 to pi. Remember, this is 0, pi over 2, pi, 3 pi over 2. The inverse tangent function has a range from minus 3 pi over 2 to pi over 2. That's for the inverse tangent function. Okay? Does everyone remember that is a consequence of the function, the tangent function, having to be restricted to that initial domain where it's 1 to 1? Okay, that gives you this restricted range of the inverse tangent function. But when you plot the cotangent function, its fundamental domain shifts right by pi over 2. So for the fundamental domain of the cotangent function, it's from 0 to pi. Not minus pi over 2 to pi over 2. So now when you look for the inverse cotangent, that gives you minus 1 over the square root of 3. You cannot just go and look for the minus square root of 3 over 3 in the tangent function, because that would put you down here at 5 pi over 3, or minus pi over 3. Instead, you're going to need to come up here to 2 pi over 3, which is outside the range of the inverse tangent function. but not the inverse cotangent function. Okay? Have I thoroughly confused everyone? Okay, then let's back up and go through this again. What are we saying when we look for the inverse cotangent? We look for an inverse function of a number. Everybody repeat it with me. We've only slept twice since we've done this. Say it with me. We're looking for the inverse function of a number is an angle whose function is that number. Okay? We're saying we want the angle, that the cotangent of that angle would be minus the square root of 3 over 3, or minus 1 over the square root of 3. And you can thank the engineers for that little extra bit of confusion. Now, calculators don't have cotangent, secant, or cosecant buttons on them. That means that whenever you start having to deal with these other three functions, you have to do the math. You have to remember, well, cotangent is just the reciprocal of the tangent. So instead of looking for sine over cosine, I'm going to be looking for cosine over sine. Okay? Well, if the cotangent of the angle of this angle gives you minus 1 over the square root of 3, what angle is that where the cotangent gives you minus 1 over the square root of 3? You know immediately that it is an angle where the tangent of that angle will give you minus the square root of 3, because it's the reciprocal. Okay? But, this is the important but now. Pay attention, because this is where it starts to get confusing. So far, it's pretty straightforward. We don't have a cotangent button, we'll look for the tangent. The problem is that the inverse tangent function is restricted to an output range between minus pi over 2 and pi over 2. But the output of the inverse cotangent function is restricted to a range between 0 and pi, not between 0 and pi, not between minus pi over 2 and pi over 2. That's exactly how you should solve this. Is you stop relying on the calculator for anything except the arithmetic. You do the math. You know that you're looking for a number, an angle that has to be between 0 and pi, and it has to have a tangent of minus the square root of 3. Well, if you go to your calculator or the unit circle, you're going to find in the output range of the tangent function, here is where the tangent is going to be minus the square root of 3. But this is not in the range of your inverse cotangent function. So you add pi to it. That brings you back, or subtract pi from it. Either way. You end up back here at 2 pi over 3, where the tangent is also minus the square root of 3, just not within the range of the inverse tangent function. But it now is in the range of the inverse cotangent function. And so that gives you the angle two pi over 3. And is that what the book says the right answer is? Oh, it's so easy. It's convenient when the book agrees with me. What was the number of this problem? 40? Yeah, okay. 2, 43, yep, 2 pi over 3. Okay. Everybody good with this now? Or is there any part of this that still got you perplexed? The algorithm that you should follow in your mind when you're solving one of these is first find the range that you're going to be looking for your angle in. In this case, you know that you need an angle that's somewhere between 0 and pi, because that's the range of your inverse function. That is the fundamental one-to-one domain of the original function. You start there, then you start thinking about, okay, what is the cotangent function? It's just the reciprocal of the tangent function. Where in the domain of 0 to pi radians will the tangent equal the square root minus the square root of 3? And that gets you to 2 pi over 3. But you have to use the unit circle and do the math in your head, sort the angles in your head. If you go to your calculator, you're going to get minus 2 pi over 3 as your answer, or 5 pi over 3, which is not the correct answer because it's not within the range, within the range of the inverse cotangent function. So, there are two things you need to understand from this. You need to understand, first of all, why 2 pi over 3 is the right answer, but you also need to understand why 5 pi over 3 is the wrong answer. Okay? 5 pi over 3 would definitely give you the cotangent of 5 pi over 3 would definitely give you minus 1 over the square root of 3. But it is not in the range of the inverse cotangent function. That was, if you'll recall, that was the whole reason that we had to restrict the original functions to a limited domain to get a limited range of output on the inverse functions. Otherwise, you would have an infinite number of answers for every value you plug in. And that would not be a function. And it would make your computer smoke. What did they call that function in the old Motorola 64 processor family? I think it was instruction hexadecimal 61. It was called HCF, halt and catch fire. It was, if you ever issued that instruction to one of those processors, that's it. You either unplug it, reboot it, because it's just going to sit there and grind until it overheats and burns up. That's what happens if you try to solve a function that's not a function that gives you infinite results. The processor will just never stop finding results. Kind of what infinite means. Any more questions about the homework? Before we go further, has everyone signed in? Is anyone here one of the people who did not get back their homework yet? What? Anthony Lee? Let's see, Megan Walker, Zach Woodard, Stephen Turner, Jory Owens, Kyle Kohler, Jacob Sanchez. That's you. All right. Matt Letney. Okay. I don't see anything for Anthony Lee. There you go. All right, let's move on to this week's material. First thing I want to do, because it's going to be important when we get into the next section, I want to take a look at writing a trigonometric expression as an algebraic expression. Basically means I want to show you how this works when you start doing substitution. If you want to follow along in the book, we're going to look at example 6 on page 205. It says, write sine of the inverse tangent of u as an algebraic expression of u. Well, the first thing we're going to do is we're going to substitute inverse tangent of u. Say it with me. What is an inverse tangent? When you look for an inverse function, you are finding an angle whose function is u. So we are looking for an angle theta. So we substitute sine of tangent, inverse tangent of u as sine of theta. Now the rest of this, they're just doing a whole lot of they're doing a whole lot of substitution here that, frankly, to me is kind of superfluous. You got it there. You've substituted inverse tangent of u as an angle theta. You've got that's about as simple as you're going to get it, but they want it as an algebraic expression of u. That's a u, not a mu. All right. Well, this means theta is the angle such that the tangent of theta is equal to u. All right? And let's see, what range are we restricted to? We're restricted to minus pi over 2 to pi over 2. No, that would be inclusive, wouldn't it? No, it wouldn't. Okay, and u in the range in minus infinity to infinity. Now, the first thing they do is they may make note that that a cosine of theta divided by cosine of theta is equal to anybody? Anything divided by itself is 1. So we can multiply sine theta by 1 and not change anything, right? So we multiply sine theta by cosine theta over cosine theta, and that's still equal to sine theta. Except sine theta divided by cosine theta is equal to tangent theta times cosine theta. Okay, what is cosine theta also equal to? Cosine theta is equal to 1 over secant theta. So this becomes tangent theta divided by secant theta, because we're just multiplying by 1 over secant theta is cosine theta. Now you get to a point where you need to use one of your trigonometric identities. Hi. Megan Walker. I'm on a mission to empty my folders. Oh, there you are, right on top. Now we need to make use of one of the trigonometric identities. And I don't want to just should be back here somewhere. There it is. On the inside cover of the back inside cover of your book, or somewhere near the back of your book, if you have the paperback, there's a table of fundamental trigonometric identities, one of which tells us that, where'd it go? There it is. Tangent squared theta plus 1 is equal to secant squared theta. Did y'all all find this identity in the back of your books? Okay. So if we take the square root of both sides, we get the square root of tangent squared theta plus 1 is equal to secant theta. And that means we can now rewrite this as tangent of theta divided by the square root of tangent squared theta plus 1. Is everybody with me so far? Okay, well, if you go all the way back to the very beginning, we already saw that tangent theta is equal to u. That was one of our original. So this becomes u divided by the square root of u squared plus 1. Okay? Now, that probably seems like it was a big, long, drawn-out ordeal. A lot of dog and pony, a lot of jumping through hoops for very little reward. If this was all it was to it, then that would be true. In the section we're fixing to start, we're going to find out that this is a very handy thing to be able to understand how to do. So, before we go on any further, I want to make sure, does anyone have any questions about what we just did and how we did it? How did we get from sine of the inverse tangent of u equaling u over the square root of u squared plus 1? Does anybody have any questions about how we got there? What we did? How we did it? Maybe why we did it, but just, have a little faith and be patient and we'll get to the why. All right. Well, then let's start on section 3.3, trigonometric equations. Now, start off with a whole clean board here because it's going to seem like we just abandoned everything we just went through. Let's look at example 1 in section 3.3. Okay, believe it or not, we're working towards a goal here. All right? The idea here is to show you how to solve trigonometric equations. Okay? Now, up until, so far we've been looking at these inverse functions and, okay, not that big a deal. The inverse function of a number is an angle. What angle would give you that function? Go look at the unit circle, check your restricted ranges, you're good to go. But in the general case, when you're solving trigonometric equations, you have an infinite number of solutions. How do you find an infinite number of anything? How do you work with that kind of a function to find those kinds of solutions? Stop and think about it like that for a minute. Once you've taken your mind away from the calculator crutch that you can't just punch in numbers and get answers. Okay, you have to do the math yourself. All of a sudden it might dawn on you that, hey, wait a minute. Solving these things might be a little bit, maybe not be as trivial as it seemed up to now. How do you find an infinite number of solutions of anything? That's what we're working towards. And it actually is a very simple process to go through, but you have to think about every step that you're going through and know why you're doing it, how you're doing it, why you can do it, and More importantly, when you can't. So let's start with a very simple problem here, and let's just look for a solution. And we're not even going to try to find a solution. We're just going to check to see if pi over 4 is pi over 4 a solution of 2 sine theta minus 1 equals 0? How would we solve that? Simple, straightforward proposition here. We've already been given a result. Is pi over 4 a solution to that equation? Well, let's just plug it in. 2 times the sine of pi over 4 minus 1, is that equal to 0? What's sine of pi over 4? 1 over the square root of 2, right? I'm sorry, 2 over the square root of 2 over 2 for the engineers. So is 2 times square root of 2 over 2 minus 1 equal to 0? Well, the square root of 2 minus 1 does not equal 0. So, no. That's it. Pi over 4 is not a solution to that equation. What about pi over 6? Well, let's change that to sine of pi over 6. What's the sine of pi over 6? Okay, well, sine of pi over 6 is 1/2. The 2's cancel. 1 minus 1. Yep, 1 minus 1 actually does equal 0. So yes, pi over 6 is a very important little article right there. A solution to 2 sine theta minus 1 equals 0. But the article is all important. Pi over 6 is a solution to that equation. It is not the solution. Why not? There's a whole infinite number of solutions to this equation. Look at your unit circle. Pi over 6 had sine of 1/2. So would 5 pi over 6. Right? So we know that just in the fundamental period, the first 2 pi of sine theta, there are 2 solutions to this equation. Pi over 6 is a solution. 5 pi over 6 is another solution. and there are an infinite number more. Because this function sine repeats every 2 pi. That means pi over 6 is a solution. Pi over 6 plus 2 pi is a solution. Pi over 6 plus 4 pi is a solution. Pi over 6 plus 6 pi. In general, pi over 6 plus k times the fundamental period of the function, 2 pi. What if this had been based on what if this equation had involved a tangent? And the period would not be 2 pi, the period would be pi. But the same thing would hold. The full solution set would include not only pi over 6, but pi over 6 plus k times 2 pi for k equal any integer. But that's not all. Is 5 pi over 6 part of this solution set? Pi over 6 plus k2 pi? How? What k can you plug in? What k integer k can you plug in there to get 5 pi over 6? Say again? There is no multiple of 2 pi that you can add to pi over 6 and get 5 pi over 6. What if you add the first integer, 0? Well, 0 times 2 pi is still 0, so it stays pi over 6. What if k is 1? Well, 2 pi is what? That's 12 pi over 6. So pi over 6 plus, for the k equals 1, this would be 13 pi over 6. So you've only added one multiple of 2 pi and you've already shot right past 5 pi over 6. By a whole pi. Hopefully it was pecan. Oh, come on, people. That deserved at least a giggle.
It was some kind of pie.
It was some kind of pie.
There's a pie out tonight, by the way.
Is it pecan? Okay.
That's what I think.
Future farmers? Okay. Where? Okay. Point is, to get the full solution set, it's not sufficient to find a solution. It's not even sufficient to find a solution and all of its multiples. You have to do 2 things. You taking notes? 2 things. You have to find every solution in the fundamental period. And then add every possible multiple of 2 pi to both of those. Or I'm sorry, go ahead.
This is actually a different solution set to the same.
No, this is all one solution set. And it is an infinite solution set. You now add every integer multiple of 2 pi to both solutions from the fundamental period. And that is the entire solution set. In other words, if you're writing it as a set, it would be, you got to put in your curly brace, and then you write pi over 6 plus k 2 pi 5 pi over 6 plus k 2 pi for k equals any integer. And then close your set. That is the full and complete solution set to this equation. 2 sine theta minus 1 equals 0. And there are an infinite number of solutions. You understand why it's just one solution set, not two? Because this is one subset of the full solution set. This is a completely unique and distinct subset of the same solution set. It's the union of both that forms the complete solution set to that equation. All right? Any questions? In your homework, you're going to find where they say, once you find all of the solutions to this equation, list 6 examples or 8 examples. Well, how would you do that? Well, let's see. Pi over 6 plus minus 1. That's an integer, right? Times 2 pi. That's one solution. What would that be? You're adding fractions, so 2 needs to be over 6. That would mean 12. So minus 12 over 6, that would be 1 minus 12, that would be what? Minus 11 pi over 6. You could write pi over 6 plus 1 times 2 pi, which would put you to, what, 13 pi over 6. I think we worked it out. Was that it? 13 pi over? Yeah. They want six examples. Pick 6 integers. 0 is a perfectly good integer. Okay? There is absolutely nothing wrong with 0. It's a great integer. It's a very easy integer to work with. Even I can do arithmetic with 0. Okay? So, pi over 6 and 5 pi over 6, there's your first 2 examples right there. After that, pick some integers, plug them in, and do the arithmetic. Of course, this was a rather simple equation for demonstrating this process and for demonstrating why it's important to understand that you're not just looking for a solution. You're no longer dealing with a restricted range, special case inverse function. You're now dealing with a perfectly good function, sine theta. But it has infinite solutions. So, now, how much time we got? Oh, good, we got another half hour. Let's look at maybe a slightly more complex equation. Who knows, we may even get some mileage out of all that pointless algebra we did a while ago. How many of you, oh, I'm hearing noises. Are we getting restless? Getting nervous? Let's look at one, well, okay, just to, they do one here, but they do one, a linear trigonometric equation. That's 2 sine theta plus the square root of 3 equals 0. I think everybody can see how you would solve that. But I want to get to one of the nonlinears. So if I rush through this, don't let me leave you behind. But I am trying to get somewhere. 2 sine theta plus the square root of 3 equals 0. Okay, well, that means 2 sine theta is equal to minus the square root of 3, and sine theta is equal to minus the square root of 3 over 2. What is theta? Break out our trusty handy dandy. You might want to put like a little post-it or some kind of bookmark that will tag page 179, because you're going to use that unit circle a lot. Where's sine theta equal to the minus the square root of 3 over 2? Yeah. Let's see. 4 pi over 3 and 5 pi over 3. There you go. You know it's in the bottom half of the circle because its sign is negative. And it's going to be 1 on both sides. So there it is, 4 pi over 3 and 5 pi over 3. But is that the whole thing? No, it is not. Because sine theta is periodic in what period? 2 pi. So we have plus 4 pi over 3 plus k times 2 pi. Five pi over 3 plus k 2 pi. 4k equals any integer. Did it tell you in the homework in a restricted range, or did it tell you to find all of the solutions?
It doesn't say all of the solutions. It just says solve each equation on an interval of 0 is less than or equal to theta is less than 2 pi.
So it's telling you right there. What does that mean? On the interval 0 is less than or equal to theta is less than or equal to 2 pi. That's right there is restricting you to just the first fundamental period. And if under that restriction, then these two are the only solutions in that interval. But they are not the only solutions to the equation. If it tells you to find every solution, you can either write it like this, or you can just write an infinite number of. And since that's not going to happen in the time limit before you have to turn in your homework, this would be my suggestion. Now, I know I did that very quickly, but that's also actually kind of demonstrates that it really isn't complicated once you understand what you're doing, why you're doing it, and how to do it. Okay? So, are there any questions so far? All right, well, that was solving a linear trigonometric equation. Piece of cake, right? Linear equation, those are easy. You know what's not easy? Because this jumped up and bit more than a couple of you on the exam and in your homework. when you are using your calculator. If you are looking for the sine of x, where x is a number, x is in what? Radians. If you are looking for sine of x degrees, then x is a number of degrees. If you do not see the little circle above the number, whether it's a number with pi in it or just a number, if you don't see that little circle, put your calculator in radian mode, because the answer will be dramatically different. Okay? I don't think it's even like Celsius and Fahrenheit. You know, at least if you're working with Celsius and Fahrenheit, if you get down to minus 40 degrees, you get the same answer with both of them. Between radians and degrees, you will never get the same answer for any of them. So make sure you put your calculator in whichever mode is appropriate for the problem. And if you don't see the little circle, it ain't degrees. Now, there better be some pages sticking together here, because I know I saw nonlinear equations in that homework set. Solving a trigonometric equation quadratic in form. And there's also a section here on using identities. We saw how to use identities a while ago when we did the secant squared is tangent squared plus 1. I don't know that we're ever going to get to it in this course where you actually have to go through and solve some of those identities to prove that they really are real. If we don't, then you might count yourself lucky, because I'm probably going to stick it into the next set, in the next class that comes through. But at the very least, go look at those identities in the back and familiarize yourself with them. For now, let's work this problem here where we're solving a quadratic equation. And there we're going to solve the equation 2 sine squared theta minus 3 sine theta plus 1. And I think they set it equal to 0. Yes, they did. Now they're saying restrict it to the fundamental period, 0 to 2 pi. We'll do that first, and then we'll look at anything beyond that. This is example 7 on page 212. So, it may help you. Remember, we did all the substituting a while ago, looking at, using u instead of the sine theta. Let's rewrite this as just a straight up algebraic equation, making the substitution that sine theta equals u. Okay, so we have 2u squared minus 3u plus 1 equals 0. Now, how would we solve that equation? Let me rephrase this. How many of you remember with dread and fear factoring polynomials? Yeah, me too. I hate factoring. It was probably, I've told y'all that algebra is the hump to learning math. Well, factoring polynomials was the hump of algebra for me. That's the worst it ever got. And, you know, and trust me, I have been much, much further beyond. I've done all of the calculi and differential equations and vector and tensor analyses, and I've done mathematics. I've published mathematics that nobody else can read. Okay? I mean, seriously, except for the people that read the articles that it got published in. Nobody, the people here at this university can't read some of the math that I've published. I hate factoring polynomials. So, I'm right there with you, okay? Just understand that. Now, who can factor this? Well, I'm going to cheat and use the book. If you factor this, you get 2u, where'd it go? Come here, there you go. 2u minus 1 times u minus 1. Did I get that right? Yeah, I did. And that, now that it is factored, piece of cake to prove that the factoring works, because you just use, anybody remember the FOIL method? First, outer, inner, last. 2u times u is 2u squared. 2u, the inner, minus 1u. Outer, minus 2u. Last, plus 1. So that's 2u squared minus 3u plus 1. Yep, it checks. Good. We have a factor. Now let's just close our eyes and move forward. Well, we know that this times this is equal to 0. How do you get anything times something else to be equal to 0? Means one of them has to be 0. Either this is equal to 0 and or this is equal to 0. If any time either one of these is equal to 0, it will be a solution to this equation. So, what's 2u minus 1 equals 0? Then that means 2u equals plus 1 and u equals 1/2. Okay. What's the other one? U minus 1 equals 0. U equals 1. Okay, so anytime u is equal to 1/2 or u is equal to 1, this equation will be true. But what is u? U is sine theta. So when is sine theta equal to 1/2? And when is sine theta equal to 1? Don't anybody look at a book or calculator. Right off the top of your head, everybody, eyes front. When is sine theta equal to 1? Pi over 2. When else? In the fundamental period of 0 to 2 pi. No. At 3 pi over 2, it's minus 1. This is one of those quadrantal solutions where you have one and only one solution in that fundamental period. That points to theta equals pi over 2. When in 0 to 2 pi is sine equal to 1/2. It's positive, so it has to be on the top. No, I said not to look on the quadrantal angle. Why do you think I let y'all have index cards? I don't memorize. I'm a physicist. I agree with Enrico Fermi when they asked him about, why he didn't study high energy physics. He said, if I wanted to memorize all those names, I would have become a botanist. I don't memorize. All right. What are we looking for? Sine of plus 1/2. Pi over 6 and 5 pi over 6. And that is our complete solution set for the problem. Because, I'm pointing at you, because I can't remember your name. Huh? Travis, but yeah, no. Why is this the complete solution set for the problem? Exactly. Yeah, because we're restricted to the fundamental period, the first 0 to 2 pi. So that's our full solution set. Pi over 6, pi over 2, 5 pi over 6, in no particular order. The book generally likes to list them in ascending order. I don't want to take the time to figure out which one's bigger. Now, okay, now let's go beyond the book. What is the full solution set to this problem? What? 2 pi, because 2 pi is the fundamental period here. There's another way to write k equals any integer. You remember that fancy scripted curly Q looking R for any real number? Well, you could write k equals this fancy curly Q I, meaning any integer. Don't write it. I don't want to read it, but if you run across it in the book somewhere, or maybe not this book, but in another book or paper, that's what that means. That fancy curly Q I means any integer. And since 0 is a perfectly cromulent integer, this includes the fundamental period. And that didn't even get a snicker. Did no one get the reference? Never heard the word cromulent before, huh? Huh? No, it's from The Simpsons, where they said, where the other teacher told Mrs. Krabappel that embiggens was a perfectly cromulent word.
Wasn't on the Brady Bunch either.
Wasn't on the Brady Bunch either. Someone has a real question. We replaced sine theta with U. Just so it could look at it and it wasn't too hard to read. That's all you're doing when you substitute. You're getting rid of sine theta and replacing it with X or U or T or whatever single letter you want to use, just to make the equation easier to read so you can work with it more readily to factor it and find your solution set. Go ahead.
All right, so I see that you factored the 2u squared, but then what do you do with the minus 3?
No. This term times this term equals all of this. Remember, we verified that with the FOIL method. You multiply the first, 2u times u is 2u squared, that's here, times the inner, minus 1u, times the outer, minus 2u, which gives you your minus 3u, plus minus 1 times minus 1 is plus 1. Yeah. And from there, once we have it factored, then we know one of these has, if for any time either of these is 0, then the solution to the whole equation is 0. And that's, everybody else take notes, because I promise you, he's not the only person that was looking at that and going, wait, how did he do that?
But we could still solve it if we did like the FOIL method and had it all out. And it looks like you just kind of did like a shortcut there.
Where?
With the 2u minus 1 times the u minus 1. Like
Right there.
if you write the full FOIL thing out, then we can still solve it, right? Well, he's saying not to simplify it after you FOIL it.
I don't understand.
Instead of combining the negative 2u and the negative u,
Oh, you're saying
instead of going negative 3, you put it negative
2u squared? But if you multiply it, FOIL it out, as you say, that you're multiplying this times this, that's just going to bring you back to where you started. And the whole point of factoring it is because you know it's 0, then you know one of the factors has to be 0. This will only be 0 when one of the factors, when either of the factors is 0. So now, instead of having to solve for every time this might be 0, you factor it out and you can say, okay, now when is this 0 and when is that 0? This is 0 when u is equal to 1 half or minus 1 half. When u is equal to 1 half. This is 0 when u is equal to 1. That's as simple as that. And that means that those are the three cases where where that equation equals 0 in the range of 0 to 2 pi. And that is the entire full solution set. Now, what if we wanted to take a bigger hammer approach to solving this? What would the solution be if instead of doing this, instead of factoring it and looking for the places where the factors are 0, what if we just solved this equation? How would we do that? A, B, C, minus B. So minus 2 plus or minus the square root of minus 3 squared minus 4 times 2 times 1. all divided by 2 times 2, or 4. Well, let's see. Minus 3 squared is 9. Minus 8 divided by 4. Okay, well, that's minus 2 plus or minus 1 divided by 4. What's minus 2 plus 1 equals minus 1. Minus 2 plus 1 equals minus 1 over 4. Minus 2 minus 1 leaves minus 3 over 4. Why did we get different results? Oh, that's true. That's right. That should be a 3. And that should be a positive 3. Thank you. Well, don't I feel stupid? Boy, ain't we? So 3 plus 1 over 4 is 4 over 4. And 3 minus 1 is 2 over 4, or equals 1/2. Thank you. That works much better when you use the right numbers in the right places. Told you don't trust me for arithmetic. I do math. That little idiot box does my arithmetic. That would be the bigger hammer approach. If you see an equation like this that's nonlinear and you can just factor it, then it becomes a lot simpler, because at that point you know that in order for it to be equal to 0, one or both of the factors must equal 0. And any time either of them equals 0, you'll get the whole equation will be 0. Now that's just like I said, 0 is a perfectly cromulent integer, and it makes arithmetic very easy. Anytime you multiply anything by 0, it's 0. And if you multiply two things that are not 0, then the answer will never be 0. Do we have any questions? Everybody all ready to go home and crank out all that homework? I'm sorry. I'm really trying. Have a good weekend, and I will see you all on Tuesday.